All right, so let's look at this example here. So we want to determine the pressure on a submarine. So let's suppose a submarine cruises at a depth of 300 meters. What is the pressure at this depth? All right, so we're going to assume that our seawater is motionless. So we're going to use the hydrostatic pressure formula to solve this problem. All right, so what is the first step in problem solving? Right, drawing a diagram. So what we've got here is, let's see, so we'll draw that line there representing the boundary between the above air and the underneath sea. And then we've got our submarine at a depth of 300 meters. All right, so there's our sketch. We want to determine the pressure at this depth. All right, so let's start listing what we know. All right, so we know our depth here below the surface is 300 meters. So that's going to be what we label as our H is 300 meters. All right, other things we need to think about. All right, so our boundary here is between sea and air. All right, so thinking about the hydrostatic pressure formula, let me just write that down so we all remember. So we've got the pressure is pressure at the surface plus rho GH. All right, so we're trying to find the pressure at whatever depth we're dealing with, which here is 300 meters. So we need to figure out our P naught. Looking here, our boundary, our seawater is at boundary with the air, so it's going to be the pressure due to the air above it, which is atmospheric pressure. All right, so we're going to need atmospheric pressure, which is 1.013 times 10 to the 5th pascals. Looks like we also will need rho, so that's the density of the fluid. We are analyzing the seawater, so we need the density of seawater. So our density of seawater is close to 1,000, but slightly more dense because there's salt in it. It's 1,030 kilogram per meter cubed. All right, and we can look that up. And then let's see. And then we've got our height, and we know G. I'm not even going to bother writing that down. All right. So luckily, this is now basically just plug and chug. So we've got the pressure is our atmospheric pressure plus our density times G. All right, so 10 meters per second squared. I think in my calculation here, I actually used 9.8. I know, it's unlike me, but so be it. And our depth is 300 meters. All right, so plugging that all in, our pressure is 3.13 times 10 to the 6 pascals. All right, what does that really mean? You might be more familiar with atmospheres instead of pascals. We can actually do a quick conversion here. All right, so we can take our pascals and apply the conversion. That 1 atmosphere is 1.013 times 10 to the 5th pascals, right, or our P naught term here. And that gives us, all right, so pascals cancel out, leaving us with just atmospheres, and about 31 atmospheres. So this is about 30 times the pressure of just atmospheric pressure, right? Which is pretty interesting. So you know if you're building a submarine for that depth or more, the materials and structure that you're building out of have to withstand that amount of pressure. Right? So hopefully that example was quick, but had you see how you can, what it means to use this formula.